Well, good morning. Let's see. We can just about dive in and start doing stuff, I think. Let's see. Should be looking at the screen over there. Oh, let me think. Ty, I think I graded your test this morning, and there was something I was going to say about it, but I forget completely what it was. I'll be sending those out to people here later today, and there will be a makeup assignment on it where you can redo all the problems that you missed any points on. So that'll be something that happens. And let's see, both of you are in lab group A, right? So I'll also be going out today to do that lab and shoot the balls at a bunch of different angles. So I don't know if I'll be able to provide you with the data by tonight or not. I could send
Did you say you'd send the tests out by email?
Yeah, I think I can bounce them back to people. I should be able to get that done tonight. I've got a list of things going on that I have to do today. Quite a few of them out at school, but we'll see how it works out anyway. And what else? Yeah, anyway, I should be able to send a note out to your lab group by today, I hope. What I'll do is take down the paper where you predict it. Or did you make a prediction yet? No, I don't think you did. Okay, so, but I'm gonna shoot at that angle, and then once you send me the prediction, I'll send you back the picture of where the projectiles actually land when it's launched at that angle, and you can compare it to your prediction then. Okay, well, let's dive in. I want to start today with doing a few of the problems that were on that sheet from yesterday. And then I have a kind of a worksheet that just has you do nothing more than drawing free body diagrams. And I don't know if I have it posted up there, but it's something that you might try just for practice on drawing free body diagrams. And maybe you'll see me do them today, but then see if you can do them on your own when you're just thinking about these different situations. But we'll start with this thing here. We have a 5 times 10 to the 5th kilogram rocket, which is a pretty large rocket. That would be 500,000 kilograms. So this thing would, on the surface of the Earth, it would weigh something like 1.1 million pounds. So it's a big rocket. But its engines produce a large amount of thrust, 1.250 times 10 to the 7th newtons. And air resistance is pretty large too, 4.5 times 10 to the 6 newtons. So what is the rocket's acceleration? And explicitly show how you follow the steps in the problem-solving strategy, which were on that thing that I gave you yesterday. These are out of the textbook. And I kind of have my own ways of solving problems, but they have some, and theirs are pretty good. Identify the physical principles involved. Well, in this case, the physical principles are Newton's laws of motion. So that's what they call it. Let's see, what is known and what needs to be determined? Well, in this one, I can see that we know the mass of the rocket, and so we can determine the weight of it from that. We know the upward force on it. That would be the thrust of the engines. Rocket engines push combusted fuelant out the tail end of the rocket. They push it downward. And that, because of Newton's third law, that combusted burnt rocket fuel that's pushed out the end pushes forward on the rocket. So equal and opposite forces. And so that's where that comes from. And then there's air resistance acting on this thing as well. So those are the things we know. And what we're supposed to figure out is the rocket's acceleration. So that's the what's known and what needs to be determined. The system of interest is just the rocket. And then it says draw a free body diagram of the system of interest and all the external forces. So a lot of times I'll start with a sketch. So in this case, a sketch isn't really needed, but I'll just imagine that here's our rocket blasting off of the Earth here, and it's got its nozzles that the fuel comes burning out of or something like that. So there's the sketch. For a free body diagram, I would, since it's leaving the surface of the Earth but hasn't left it yet, there's always going to be mg, and so that's a force. Now, there's an upward force on it that's the thrust of these things, and so I'll call that the F sub T, the force of thrust that's pointing upward. Then it says that there's air resistance. Now, we draw the thing as a dot here to represent the rocket, but I have two downward forces acting on it. So I just put a little, when I have two forces pointing the same direction, I just put a little extension on the dot, and I would call this the force of the air here. So those are my three forces. So that's my free body diagram. And something that's very important is that only forces are shown on the free body diagram, not accelerations or velocity. Although sometimes you may want to remind yourself the direction of the acceleration. Well, just stick it off to the side somewhere or do something like this. Okay, here's the acceleration. It's going to be upward. And so that's something that you can do. Where this really gets important is, I'm not sure just how complicated the problems get in the next chapter, but there's one type of situation where, like a car driving on a banked track, and so this would represent a wheel of the car. So these are the wheels of the car. You sketch them in black. And this is looking at an end view of the car as it's going around the track. Boy, what a great car. That one wheel is going to cause problems. So we'll pretend that one doesn't exist. Anyway, the velocity of the car is into the track. The track is banked. And so forces acting on the car, there'd be mg downward. There's a normal force, which we haven't really talked about yet. And there would probably be friction, and depending on the speed of the car, the friction can either be down the plane, parallel to the surface, or up the plane. But the acceleration of the car is in this direction. It's toward the center of the circle, and we haven't studied that yet, but that's the direction of the acceleration. So that makes things kind of complicated for a problem like that. But let's go back to our rocket problem. We know the magnitudes of these forces. We don't know mg, but we know m instead. But still, that's not that hard to do. And in a case like this, everything's in one direction, up or down. So that was kind of like what we had yesterday with the elevators. So I can just say positive is upwards, and the net force is going to equal MA. So that's the way this thing happens to work out. By the way, the net force is what you get when you add all the forces together. And you add them as vectors. So you'll add an upward vector to a downward vector. Now in one dimension, that downward vector, you just indicate it with a sign, but in general, they can be in other directions. in a two-dimensional problem. And yeah, we're mostly still dealing with one-dimensional things today. But in general, they can be that. But sometimes you would write the net force as whatever force 1 is plus force 2 plus force 3 and so forth. You've got a bunch of different forces acting together, and you add them together as vectors. So you draw head to tail diagrams for these things, or we'll learn more sophisticated means of doing it. But there's a shorthand way of writing this. It's just to use a Greek letter, capital sigma, and I don't know if you've ever seen anything like that before, but that particular symbol means a sum. And so this just means then the sum of the forces. So summing is adding. So there's a shorthand way of doing it. Now in this case, for my net force, because I can treat this one-dimensionally, I'll just say, well, the force is acting on this thing. I'll have F sub t, and it gets a plus sign because it's pointing up, minus mg, that's downward, minus this force of the air. Air resistance always is in the direction opposite the velocity. So the rocket's going up, says it's accelerating straight up, and so the air resistance is that way. So I'll have force of the air here. And that is my net force. And that'll equal MA. Now I know the mass, I know G, I'm given the value of F sub t and the other thing, and the only thing I don't know is A, and actually, I don't have to do this calculation. If I divide both sides by M, I will get this, and I'm going to bring the A over on the left side, or just reverse the order of this equation. I would have the acceleration is going to be the force of the thrust minus the force of the air, and I just reordered this, minus mg, and I'll divide everything by m, but for that last part, when you've got a fraction like this, you can split it into a bunch of fractions. I can just leave these two grouped on top of one, force of the thrust minus the force of the air resistance, divided by m minus g. Okay. So I don't actually have to calculate the weight of the rocket there. And now it's just time for plugging and chugging. So my acceleration would equal the force of the thrust, 1.250 times 10 to the 7th minus 4.50 times 10 to the 6th newtons. That was the air resistance. Divided by the mass. There it is, 5 times 10 to the minus 5th, or 10 to the plus 5th, excuse me, kilograms. And then minus G, 9.81 meters per second squared. Now, something about the way these two numbers are written, I can do something with that. This 4.50 times 10 to the 6th newtons, I can write that as, I'll just show you a trick on a piece of paper here. This 4.50, I can write that as 0.450 times 10. Does that make sense? If I multiply this by 10, it'll move the decimal point over, right? And that's 10 to the 1st times 10 to the 6th newtons. Well, 10 to the 1st times 10 to the 6th is 10 to the 7th. So I've got 0.450 times 10 to the 7th newtons, and I'm subtracting that from 1.250 times 10 to the 7th newtons. So I was just kind of doing that in my head. You can also do this on your calculator, and it's easier. In fact, let's just do that. This is too much right now. If I was doing it in my head and having to do that, I might take that shortcut. But I'll just put in my 1.25 EE7 minus, oops, I needed to start with parentheses. Oh, well, I'll show you how to fix that. 4.5 EE6. So I just calculated that denominator. I want to divide it by this stuff. So divided by 5 EE5. Unit-wise, a newton is a kilogram meter per second squared. So dividing by a kilogram gives you a meter per second squared. So this term will have units of meters per second squared, which is good because you can only add and subtract things that have the same units. And here I get actually 16.0 times 10 to the first. So, and I can keep 3 significant figures because that's how many I have down here. Oh, that's just 16.0 meters per second squared, and that's 3 significant figures minus 9.81 meters per second squared. But you know, when you add or subtract, the uncertainty is going to stay in the first uncertain place. So this has precision to the 100th place. This only has precision to the 10th place. So in my final answer, I'll only be able to keep precision to the 10th place. Okay, but I subtract 9.81. Not that the one's going to make any difference. And I get 6.2 meters per second squared. Only 2 significant figures. So the acceleration is down to 6.2 meters per second squared. So not a huge amount, but it's a big rocket. Anyway, so there's that. Any questions on that problem? Okay. Here we've got an 1,100 kilogram car pulling a boat on a trailer. What total force resists the motion of the car, boat, and trailer if the car exerts a 1,900 Newton force on the road and it has an acceleration of 0.550 meters per second squared? Well, this is a complicated problem. So I'm gonna, I think, make a sketch of this. This ought to be good. Okay, anyway, those are the car's wheels, and it kind of looks like a car from the side. Anyway, and then it's got this trailer hitch on it, and the trailer goes back here. Here's a boat wheel. Maybe comes up above there, and there's a big boat sitting on this trailer somehow. Maybe not such a big boat. Okay, so there's our situation. Now, what kind of forces do we have working in this direction? Well, if I make a free body diagram for the car, I'll have the car's weight, mg, pointing downward like that. And I'll have what we call, this is a new force for us, a normal force, which is pushing up from the road on the car's tires. Okay. And then there are some not so nice forces. One of the forces that acts, though, is the reason that a car manages to move forward is because there is friction between the tires and the road, and the friction between the tires and the road is actually what pulls the car forward. It isn't you putting your foot on the gas pedal. That's an internal force. And it isn't the engine making the wheels rotate, pushing on them. That's an internal force. The external force that acts to move the car forward is the friction between the tires and the road. The car exerts a 1900 Newton force on the road. What that means is, as the tires rotate, they push backward on the road this way, and the road pushes forward on them. And so this ends up being the 1900 Newton force. That is, it's the third law partner. It's the friction between the tires and the road. And that's 1900 Newtons anyway. We have that. And then there's going to be a backward resistive force on the car, and another backwards resistive force, that is the force of the trailer. So I'm going to label these things. This is the, I think I said the trailer twice. This one's going to be a resistive force of some sort, maybe air resistance, something like that. And then the trailer exerts a force on the car too. Okay, so that's just for the car. Now, what about for the trailer? Well, let's see. The trailer is also going to have its weight. I'll call this M sub T. It'll be the trailer and the boat times G. It'll have a normal force on it. And so I'll call this N sub T there for the normal force on the trailer. Now, the car is exerting a forward force on the trailer. I'll call that F sub car. And it's actually the third law partner of the force that the trailer exerts on the car. So we have that. And then there's going to be some kind of a resistive force here, which is going to be just F sub REST, force of resistance acting on the trailer. So we got a complicated situation here, except nothing happens in the vertical direction. The car doesn't jump off the road and it doesn't fall through the road. The trailer doesn't jump off the road and it doesn't fall through the road. So these vertical forces add to zero. And so I don't even have to worry about them for figuring out the resistive force things that are going on here. And I can set up a single equation for each of these things, and I'll show you what they look like here. I'm going to choose the leftward direction, this is the trailer, to be the positive direction, but I'm going to write these things down as, well, no, I'm going to just do everything as a scalar, but anything that points to the left gets a positive sign. Anything that points to the left or the right gets a negative sign. So to the left, I've got that 1900 Newton force. And then here I've got minus the force that the trailer exerts on the car. And then I've got minus whatever resistive force is acting on the car. And this could be something like air resistance. We're not really told what it might be. But that's what I have for the car. And this will equal the mass of the car times the acceleration of the car. this is Newton's second law. I've got all the forces, I'm adding them together, but if they point to the right, they get a minus sign. And that'll equal ma, mass of the car times the acceleration of the car. Then I can write something similar for the trailer. Forces to the left get a positive sign. Well, I'll have the force of the car acting to that direction minus the resistive forces. Whoops, I'm going to put RES car. These are the resistive forces acting on the car. So the force of the car pulling on the trailer goes that way, minus the resistive forces that are acting on the trailer. And that will equal the mass of the trailer times the acceleration of the trailer. So there's two equations, but I can simplify this. If I add these two together, the car and the trailer are connected together. They're going to have the same acceleration. So I'm just going to let each of these things be represented by A. And I'll just call that the acceleration of the car and the trailer. So I'll have that. And we know what it is. It happens to be 0.550 meters per second squared. So we know that. Also, this is the force that the trailer exerts on the car. Its third law partner is the force that the car exerts on the trailer. This one is positive because it points to the left. This one's negative, it points to the right. But those are third law partners. When I add these two equations together, they're going to go to zero. And I'm going to do that. If you have two equations, you can add them together. You can always add the same thing to both sides of an equation. On the left side of this top equation, I'm going to add this. On the right side, I'm going to add something equal to this, which is this. And it's okay to add equal things to both sides of an equation. It looks different on one side than the other, but because they're equal, it's okay to add them. So now here's what I get. I'll have 1900 newtons, and I'm adding these together. The force of the trailer and the force of the car are opposite and equal because they're third law partners. Those combine to zero. And so I'll have minus the force of resistance that's acting on the car minus the force of resistance acting on the trailer. Okay, that's the left side. Got everything taken care of. On the right side, I just have the mass of the car times its acceleration, and just plain A, plus the mass of the trailer times its acceleration. Now, what in the world are they asking for? They're asking for what total force resists the motion of the car, boat, and trailer if the car exerts a 1900 newtons, blah, 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 and produces an acceleration of 0.550 meters per second squared. Oh, and the mass of the boat plus the trailer is 700 kilograms. So we have that. Well, here's what we're after. We want these things. So let's just bring them to the right side, bring these over to the left side. And by the way, these two things I can write as mass of the car plus the mass of the trailer. And the mass of the trailer will include the mass of the boat times A. I just don't want to write mass of boat and trailer. That would be a pain in the neck. Okay, well, when these come to the right, they'll be positive. When these come to the right, left, they'll be negative. So I'll have 1900 newtons minus the mass of the car plus the mass of the trailer times the acceleration, and that will equal the force of resistance acting on the car plus the force of resistance acting on the trailer. And this is what I want, is this sum here. And so let's go ahead and do it. Plug in the numbers. 1900 newtons minus, well, the combined mass of the car and trailer, the boat and the trailer is 700 kilograms. That of the car is 1100 kilograms. And I'm just going to add those together in my head. 700 plus 1100 is 1800. And then the acceleration that those two are experiencing is 0.550 meters per second squared. And that will equal, can you still read me? Okay, looks like it. That'll equal that resistive force. And I'm just going to call this F resist total because it's the resistive force on both those things. And here I'll just plug this into the calculator. 1900, whoops, turn on the calculator first. 1900 minus 1800 times 0.550, and I think we'll be good to go here. And it ends up being about, let's see, 910. Boy, it sure is hard to know where the significant figures lie here. I should actually have to round this off to the nearest 100 because this is only to the nearest 100. This is only to the nearest 100. This is only to the nearest 100. So I can only keep to the nearest 100, which ends up being that resistive force is equal to 900 newtons. A kilogram meter per second squared is a newton. So newtons minus newtons. And that'll be the total resistive force. So, which is actually a fair amount. A 900 Newton force is, let's see, well, not really that much, I guess. Converting units on that, 900 newtons times 1 pound over, I can remember this conversion factor for some reason, 4.448 newtons is going to be just about 200 pounds. So to the nearest 100. So that's how much that is. Okay, excuse me, the last part of this, it asks, what is the force in the hitch between the car and the trailer if 80% of the resisting forces are experienced by the boat and the trailer? Man, they're making this complicated. Well, let's see what we can do with this. The total resistive force is 900 newtons. 80% of it is experienced by the boat and trailer, which means the resistive force on the trailer must be 80% of that 900 newtons. Okay, does that make sense? Then, considering what's going on here, this F sub car is the force that's acting on the hitch, and so I can set up an equation just for the trailer, kind of like what I did before, but it'll be F car minus the force of resistance on the trailer. Actually, I'm copying this equation right here. Okay, and I want to know what force the car exerts on the trailer. That will be the force in the hitch between the car and the trailer. So that'll equal the mass of the trailer times the acceleration. Well, this force of resistance by the trailer has a magnitude of, or on the trailer, has a magnitude of 80%. That's 0.80 times the 900 newtons. And I don't like problems like this that are so loose on the significant figures that you have to throw everything away. This just gives you 700 newtons is all it gives you. So it would be 720 newtons, but we only have one significant figure on this thing. So that's it. But anyway, the force that the car then has to exert on this is going to equal the force of resistance on the trailer plus the mass of the trailer times the acceleration of the trailer. So we'll just plug everything in here. We just calculated this. It's 700 newtons plus the mass of the trailer and boat was 700 kilograms. And the acceleration of the boat is 0.550 meters per second squared. So 700 newtons plus 700 kilograms times 0.550. Let's see, to the nearest 100, I would get 1100 newtons on this thing. So that would be the force in the hitch when you're accelerating like that. That was a long problem. Quite a bit to that thing. Okay. There's a last problem that I printed yesterday that has to do with the tension on the wire in a set of braces, but I think I'm going to skip that and move on to these free body diagrams right now that let's see, take all of these away that I printed off, and we'll see what we can do with it. For a free body diagram, there's some sort of accepted rules. You draw the object as a box. You draw every force that's acting on the object as an arrow originating on the box. So, or a dot. Let's see. So here are the rules. Object as dot. And sometimes we monkey with these rules if we happen to have two forces acting in the same direction, but forces as arrows pointing in their proper direction. Pointing in proper direction. Oh, and I forgot to say originating on the dot. Originating on dot and pointing in the proper direction. So we have a book at rest on a tabletop. Okay. Now, unless told otherwise, you can always assume that this is taking place on Earth. And something you can always write on Earth is this downward arrow, mg. Okay, that's what I call the low-hanging fruit. And when I ask these in class, I'll ask, all right, what's one of the forces that's acting here? And if somebody yells mg pointing downward, then yeah, that's the low-hanging fruit. Now, this is just sitting here on a tabletop. When that's the case, it's not accelerating, so there's got to be a force opposing this, and we call that force the normal force. And It's the atoms in the top of the tabletop repulsing the atoms in the bottom of the book, and they push up on the book. So add all of those things together and you get what we call the normal force. It's perpendicular to the surface, and we just use a lowercase n to stand for it. That's it. Those are the only two forces that are acting on the book. And so we don't have to worry about anything else. Okay, next one. The girl is suspended motionless from a bar which hangs from the ceiling by two ropes. Sometimes there are distractors in these things, by the way. So then it says a free body diagram for the girl in this situation looks like this. Well, for the forces, the only force at a distance that we're going to deal with is gravity. That's the mg part. And so the girl is hanging from the bar. The only thing she's in contact with is the bar. And so for the girl, the forces that act, pick the low-hanging fruit first. So if I ask, what's one of the forces acting on the girl? mg. So that's the low-hanging fruit. Okay, acting downward. The only thing she's actually in physical contact with, although that's kind of a fuzzy definition. Gravity acts at a distance. Every other force has to act from essentially contact. The bar is going to be what she's connected with. And so we'll call that the force of the bar. Okay, it's the force that the bar exerts upward on her. Right. Now, it doesn't matter that the bar hangs from the ceiling by two ropes. Those ropes are attached to the bar, not to the girl. So we ignore this stuff. That's a distractor. So that's what we have. Now, I should probably, some people will make a big deal out of drawing the arrow lengths so that they represent the force of the strength of the force very well. I'm not that fussy about it. If you get them pointing in the right direction, that's the thing I'm mainly concerned with. But I drew this mg arrow on this one a little bit longer than I drew this. So you could, if you were going to be worrying about that, make the force of the bar be a longer arrow to show that they have the same strength. Sometimes you'll get scale diagrams that, in fact, there's one on this week's homework assignment, if I remember correctly, that make you think about that stuff. But sometimes it doesn't really matter. If you get the directions right, that's what'll matter. Okay, number 3 here. An egg is free falling from a nest in a tree. Neglect air resistance. A free body diagram for the situation looks like this. Well, what we have here is an egg. That's kind of a round egg. It's falling through the air like this. And at any given instant, it'll have some velocity and it's falling toward the ground. Those are supposed to be just streamlines of air, something like that. They're not actually connected. Well, what have we got for forces acting on this thing? Unless otherwise told, assume it's on Earth, and it's a nest in a tree, so I think we're on Earth. Okay. And since that's the case, one of the forces is mg. Now, what other force could possibly act on something that's falling from a tree? Sometimes air resistance could be counted, but in this case, they say neglect air resistance. That means ignore it. Pretend it just doesn't happen. And in that case, this is the only force that can act. So that's all there is to this particular free body diagram, is just mg downward. Okay, we'll just do this last one here. And then there's still, I think there are 10 in here. And give them a shot at night. I'll post these up there with today's video. as soon as I get it done processed. But a flying squirrel is gliding from a tree to the ground at a constant velocity. Now it doesn't say this, but I'm going to assume, so here's the ground down here, and we've got this tree here, and the tree's got a bunch of branches sticking out and stuff like that. I'm going to make the assumption that the squirrel isn't gliding straight down, but is gliding down at some kind of an angle. So here's Rocky here. And let's see, squirrels have long tails. So there's the squirrel's tail gliding down here. Constant velocity, well, that to me means in this direction. Okay. Now, if the squirrel is gliding with constant velocity, then the forces acting on the squirrel have to add to 0. So that's something that we have to have going on. Well, what are the forces acting on the squirrel in this case? It's got mg acting downward. And then it will have air resistance that is acting opposite the velocity. Let's see. So if it's gliding downward at like that, we have to have that going on. And I'm going to call that F sub resistance there. But by those two, that would give us an acceleration. If you add these two together as vectors, you would end up with an acceleration down in that way. So there must be another force acting on the squirrel. And that other force can be lift that's provided by its wings. So this could be the force of lift provided by the wings of the squirrel. And when you add these three things together, they add to 0. Since this one points down, that tells me that the component of the resistance that's up plus the component of the lift that's up must combine to equal this thing. And because it's not accelerating sideways either, it says constant velocity. That tells me that the rightward component of the lift must equal the leftward component of the air resistance. Otherwise, they wouldn't cancel out. So this one's kind of tricky to try and understand. But any questions on any of those? Read about free body diagrams in the book. And again, I'll get this thing posted sometime this afternoon. And you can try the ones 5 through 6 and just try to think your way through these things. Some of them are kind of tricky, but always remember you're only concerned with the forces acting on the object, not the forces acting on something that's attached to the object. So that's like the girl hanging on the trapeze or on the bar. You don't care what the bar is attached to or how it's held up or anything. All you care about is the fact that the bar exerts an upward force on the girl, and that's what holds her up while gravity is acting downward. So that should do. This is a funner activity to do in the classroom. I've got a bunch of little whiteboards that I can have at each table, and people can draw these things and talk them over while they're doing them. But I'm not sure just how to make that work here. So I'll stop there and
I have a question. Have you finished grading the tests yet?
Let's see. I have 2 that people haven't. The PDF files they sent me were corrupted, and so I have to figure out what to do about that. But And anyway, but I've got the 3 of yours all graded, and I'll be sending those back to you here sometime today.
Oh, yeah.
And then,
Huh? Yeah.
oh, there'll be a makeup assignment on it, which is to take any questions that you didn't get full credit on and do a good solution for it and turn that in. And doing that, then you get to split the difference between the points that you got on the first try and the points that you'll get on the retake. So you can make up to 50% of any points you missed on the test, if that makes sense. So
I have like one more question.
okay, yeah, go ahead, Ben.
So there's on the WAM app, there's question 12, which I don't think we've gone through too much on how we would do that.
You mean on sapling?
Yeah.
You've been
All
taking
right.
math classes.
Yeah.
Yeah, it's all WAMAP on that. Let me look at that. Let's see. When's it due? Or when did I say that stuff is due?
It's due today, I think.
Oh, I can bump that by another day.
Yeah, because it looks like we're still kind of going through a lot of this stuff, like the free body diagrams especially.
Yeah.
Yeah.
Let's see, control dot. Whoops. There we go. Okay, weekly homework 1 on Newton's laws. Okay, 12 is, yeah, we should do a problem like that tomorrow. These were supposed to be just on chapter 4, but that looks more like a chapter 5 problem to me. So, and then what's 13? Let's see. Yeah, that's just 13's doable with what we know. 14 is kind of doable, I think. It's
You might check question 9 too. 9 is like circular motion, from what I was told.
oh, okay, which we have not done yet either. Whoops, that's 10, I think I'm looking at there. Atwood's machine. Whoops. Are you sure? Or which, let's see, let me just get out of here. Oh, close that. Question 9. No, it isn't. It's not circular motion, I don't think. Because they're all just at rest. Oh, there is one that's circular motion. Yep. Scenario H. Yeah, so I don't think there's any circular motion in chapter 4, as far as I know. I think that's held until we get into chapter 5. Oh, it's actually in chapter 6 is where circular motion shows up. Is there any way? I think I'll have to take that one off there. What question is that? Oh, remove question from the assessment. Yeah, I'll knock 9 off of the assessment because that one, save it for the next assignment. So we'll do that. Okay, Well, you got the assignment knocked down by one. So it's just the two connected blocks there, which we can look at a problem like that tomorrow. I did one with the Atwood's machine the other day, and I think maybe chapter 4 does a few like that. I'm not sure, but I don't think so. It's pretty simple. But we can do an inclined plane problem like that tomorrow, and I'll bump the due date on this thing back while I'm at it. Oh, you can't see me looking at these problems. Let's see, available from, what's the date? Today's the 11th. Yeah, I'll just change that by 1 day. Okay, so that homework's due tomorrow. And I think that's all I have to do to change its due date. All righty, good to go.
Thank you.
Okay, and I'll see you tomorrow.